All right, I see that, Yolanda. Go ahead and switch over.
Okay.
Thank you. All right, now let's rock and roll. Hello, everyone, and welcome to our VEEPS program, our virtual exploration experiences with a planetary scientist. And welcome to our Asteroid Day program. We have the phenomenal Dr. Tracy Becker. She's going to be our wonderful speaker tonight to engage your student, to grade your family, to engage your little scientists in what's so great about Asteroid Day. So we are streaming on YouTube, the Lunar and Planetary Institute YouTube page, as well as we are accepting questions using Q&A, and Dr. Becker has agreed to have questions throughout. So always feel the need, if you feel inclined to ask a question, go ahead and post them in the Q&A, and we'll be asking or answering questions throughout. So feel free to use that tool to your advantage. Again, welcome to our Asteroid Day program. Before we get started, I'm going to launch a poll for everyone to answer. I'm going to launch a poll question. All right, and so our first poll question that we're going to answer tonight is, did you know that last year NASA landed a spacecraft on an asteroid? Did you know that? How is that possible? I don't know, but guess what? Dr. Becker is going to give us some context to this question, and we're going to start closing the polls in 5, 4, 3, 2, 1. Dr. Becker, could you give us some context behind this question, please?
Sure. Yeah. So so NASA, when we say landed on the asteroid, really we kind of did a touch and go. So NASA sent an asteroid, a mission called OSIRIS-REx to the asteroid Bennu, and it was equipped with the capability to basically stick a hand out, they called it tag SAM, onto the surface of the asteroid and collect some of the material. And that material is now on its way back to the Earth so that we can better understand the asteroid and what it's made out of and what the pieces of its surface look like.
All right, well, awesome. Well, I did not know that until now, but thank you for sharing that. And Dr. Becker, I am going to, I want to allow you to introduce yourself. My name, everyone, is Sherelle Webb. I am the public engagement lead at the Lunar and Planetary Institute. And as you can see, these phenomenal, beautiful faces on this panel, I have with me a few others. Yolanda Ballard, she is our everything. And Yolanda, if you want to come off mute and introduce yourself, please do so.
Hello, everyone, and thank you for joining us today. I'm Yolanda Ballard. I am the program coordinator for LPI, and I basically do all the support work for the entire education team. So glad to have you here, and thank you.
Awesome. And then I have the newest partner in crime. Her name is Grace. Grace, would you please introduce yourself?
Sure. Hi, everyone. We're so glad to have you. Happy Asteroid Day. My name is Grace Bodwin, and I'm an education specialist here at LPI. And with this event, my job is just to back up Ms. Sherelle with this amazing program and help provide a little bit of support for Dr. Becker to tell us all about asteroids today.
Awesome. And then Andy Shaner. This is my work husband, Andy Shaner. He is awesome as well. Andy, take it away.
Oh, well, thank you, dear. So my name is Andy Shader. Well, it doesn't really matter what my title is. I'm an education specialist here too at the LPI. And today I am going to be demoing an activity for you related to asteroids and how we can learn about what they're made of.
All right, Andy. And last but not least, Dr. Tracy Becker. Go ahead and introduce yourself to us.
Hi, everyone. So my name is Tracy Becker. I work at the Southwest Research Institute, which is here in Texas, in San Antonio. And I study asteroids. I study Jupiter's moons. I study Saturn's rings. I kind of love everything about our solar system. So that's sort of, I study all of the above. And I'm really grateful for the Lunar Planetary Institute for inviting me to speak today.
Absolutely. Anytime, Dr. Becker. Please believe me, anytime. All right, we're going to first start this off with Andy. Andy, go ahead and introduce your activity to us before we get into the presentation.
Okay, thank you. So what I've got here with me are a couple of models, if you will, of two asteroids. So let me get my phone camera going here. There we go. So I have uniquely labeled them 1 and 2. Maybe do it. Oh, that's better. There's 1 on the left and 2 on the right. So they're about the same size. They're about the same volume. But what we're interested in is, what does the interior of these asteroids look like? Okay. In Dr. Becker's presentation, she's going to mention that a little bit about how asteroids may or may not be structured on their inside below what we can see out on the surface. So in this case, they look similar, at least in terms of their color, about their size, and with our models here. And though they're different in shape, they look similar, but they may be different on the inside. And what I'm going to do, and actually this particular method we can do, there's a way you can measure its temperature, so to speak, of the inside of an asteroid. And so what we're going to do is, as soon as I get done talking, I'm going to start taking a temperature measurement of each of these asteroids about every minute while Dr. Becker is presenting. And then when she's done, we'll come back to me and we'll look at the data I recorded, and then we'll talk about that. So, thank you.
Thank you, Andy. Now, Dr. Becker, would you please take us away?
You bet. Let me just share my screen here and go into presentation mode. Can you see my slides? All right, awesome. Great. So I am, again, excited to share with you all a little bit about what are asteroids and why do we study them for Asteroid Day 2021. So the big question, maybe all of you are thinking, are what are asteroids? Perhaps some of you know, but for a refresher for some and maybe new knowledge for others, asteroids, to understand what asteroids are, we have to go back to the start of our solar system. So our solar system began, just like other solar systems began, as kind of just a region of gas and dust, kind of in a big kind of nebulous ball of material, just material out in space. And something happens that kind of triggers gravity to start kind of pulling all this material together, and the whole thing starts to kind of spin around, and things start to coalesce or combine in the center of this region. And that ultimately ends up being the central star. In our solar system, we call that star the sun. And then there's still other material kind of left over on the outside around the sun that's still kind of orbiting around, and we start to kind of flatten this the disk. So you can see it goes from A to B to C, which starts to look a little bit more like the solar system that you might have seen images of before. And ultimately to D, which is where we are kind of get these defined planets, where all of the gas and dust either kind of gets rolled up into the planets or gets rolled up into the sun or kind of gets spewed off in other places. But there's these kind of what I like to call leftover pieces, which are the asteroids. And so for those who are here, families, perhaps your parents, if you're a young kid, if you've ever built an IKEA chair or an IKEA bed, perhaps you may have built this beautiful, new furniture, and somehow there's some pieces left over. And so I like to compare the asteroids to the leftover pieces of an IKEA furniture. But this is important, right? those leftover pieces actually formed during the earliest stages of the solar system. So studying those asteroids actually is really important for telling us how asteroids may have formed and how they've moved around since the beginning of the solar system. So to answer the question, the asteroids really end up being these small rocky or possibly metallic objects kind of floating in space. And most of those asteroids we find in the region of the solar system called the main asteroid belt. This is the region between, it's kind of outside of Mars's orbit, so you can see where Mars is here, and inside of Jupiter's orbit, which is here. And that's kind of the main place where a lot of the asteroids reside. That's not the only place. There are certainly asteroids that can be closer, and there are asteroids that can be much, much, much further from the sun than that region, but that's where a lot of the asteroids are. And so now we know a little bit about what they are, but why do we care? Why do we want to study them? The first thing is, of course, the most important in my mind is science. You know, as I said earlier, some of these objects formed in the very early stages of the solar system, and they just didn't get incorporated into a planet. And so really what they are kind of these nice pristine relics of the original solar system. How they've moved around and things like that also tell us about how the planets formed and how the planets have actually moved around in our solar system. But importantly, the asteroids are also very different from one another in many cases. They come in different shapes, which you can see here. And they also come in different sizes, and they kind of can come out in different forms. And so this is a little bit what Andy was talking about at the beginning, which is that some of these asteroids are kind of these solid rocks, and they're just kind of pure chunks of rock or metal. Some of them might be differentiated like a planet. So some of them might actually have a core, a mantle, and a crust, if you've learned about that already in school, like the Earth has. And some of them are what we call rubble piles, where they're all kind of just very loosely bound pieces of rocks that are all kind of stuck together a little bit by gravity. But they're not really a cohesive solid rock. They have a lot of porous space or space in between the rocks. But even though they might be that on the inside, they may look like a kind of a more solid body from the outside. So we need to know a lot about these, you know, why are these asteroids so different? And what does it tell us about how those asteroids formed, how they may have been impacted in the past, and what they might mean for our future. So another reason we study them is for exploration. We want to, we may actually end up being able to use some of the resources on asteroids. There's one asteroid where a lot of people's minds go to when we say resources, which is like gold and silver and metal. And there's an asteroid called Psyche, which is the target of an upcoming NASA mission that we believe is kind of purely made out of metal. And the newspapers like to say, oh, it could be worth, you know, 10 quadrillion times the Earth's economy. But I don't really think of those kinds of resources when I think about resources for asteroids. I think more of water, because we can use water to refuel our rockets. So we've seen kind of possible salty water on one of the asteroids called Ceres, which is the largest asteroid, and in fact is a dwarf planet in our main asteroid belt. So you can imagine rockets kind of stopping over at some of these asteroids, refueling if there's enough water there, and then moving to the outer part of the solar system. So there's a lot of potential that these asteroids could actually help us explore the deeper parts of outer space. And I think very importantly, we have to mention is planetary defense. We know that about 65 million years ago or so, there was a pretty powerful impact by an asteroid or potentially a comet that hit the Earth and wiped out the dinosaurs. We want to be able to study these asteroids so we know if any of them are on their way to the Earth. And maybe we, you know, many people like to say that the dinosaurs didn't have a space program, but the humans, we do. So we know that these impacts have happened in the past. And in fact, what you can see in the bottom left here is a picture of the Tunguska event, for which we are officially celebrating with Asteroid Day. So Asteroid Day is celebrated on this day in remembrance of the Tunguska event, which happened in 1908, which was an asteroid or maybe even a comet came in through our atmosphere and got very, very, very close to the ground, and exploded from all the pressure from its trajectory inward, and ultimately flattened all of the trees in a huge area around where that explosion occurred. It was in a remote part of Russia, so there wasn't a lot of known damage to humans or property or anything like that. But the remnant of it was certainly these flattened trees, and there were witnesses who heard the event and possibly saw it, and we have the pictures to show it. So, we know that these things can come in, and if that object had been perhaps a little bit bigger or a little bit denser, it may have actually hit the ground. We can see this in Meteor Crater in Arizona as well. This is a really well-kept crater that's out in Arizona if you've ever had a chance to visit it. And you can see how big it is compared to the little tiny people standing at the edge. Another, so we know we need to study these, right? We know we have a couple of really important reasons to study asteroids, but how do we do it? How can we learn about asteroids? So the first and easiest way is actually with meteorites. These are asteroids, pieces of the asteroids that we can find here on Earth. Here are just a few examples. This one's a very rocky meteorite that kind of looks like a lot of the asteroids that we see in the solar system. This one's a big chunk of iron metal meteorite. And so we do see some asteroids that we think are also kind of purely metallic. And we see these pallasites, which are really, really beautiful, actually. And these are kind of mixes of stone and iron and other material that's just kind of incorporated inside of the asteroids. When they come in through the atmosphere, a lot of times they break up quite a bit because our atmosphere protects us from a lot of these impacts. But ultimately, some of the pieces make it to the ground, and we can find them and we can study them. And then what we can do is we can compare them to the asteroids that we see in space. So we can use a bunch of telescopes, all kinds of telescopes, to then study the asteroids we see in space and compare them to what we see with the meteorites. So here are just a few examples of space telescopes that we use to look at the asteroids. Some really nice telescopes that we have on really high mountaintops here on Earth, so we can see the telescopes to see the asteroids. And we can use radar facilities like the Goldstone Observatory. You can see the dish here. And we used to be able to use the Arecibo Observatory as well to actually send a signal out to the asteroid and see how it reflects. So we could actually learn about the asteroids that way. And an important thing to note here, and this also, you want to keep this in mind for Andy's experiment, is that we can look at these asteroids with different wavelengths of light. So our eyes see quite a few wavelengths of light. We see red, yellow, green, orange, all the colors of the rainbow our eyes see. Those are actually different wavelengths of light. But our eyes can only see the colors of the rainbow, and there are actually way more colors out there. There are way more wavelengths of light that we can study asteroids with. And so some of these telescopes have the capability to see those colors of light that our eyes can't see. In particular, of interest here, I'll just mention this for me because I love the ultraviolet. I use the Hubble Space Telescope to study asteroids in the ultraviolet, and I use telescopes like the Arecibo Observatory to study them at radio wavelengths. But a really powerful tool is to look at them in the infrared. And this is a way that we can see not only how they reflect sunlight, but also how much heat they're kind of giving off with time. And that's what we'll talk a little bit about with Andy's experiment too. So the last way to study an asteroid is to go there. Just go straight up and look at the asteroid nice close up. We just talked about, because we had the poll question about asteroid Bennu, the OSIRIS-REx mission. This is it collecting that sample. Similarly, the Japanese space agency, JAXA, went to a different asteroid called Ryugu and collected a sample from that asteroid, and you can actually see some of that sample here. And we've been looking at some of these asteroids with spacecraft close up since the 1990s. So it's been a long time now that we've managed to actually go out and explore some of these asteroids. And there's lots more to look forward to. So I really want you all to start getting excited about some of these upcoming missions. The Lucy mission, which will launch later this year, is a mission led by the Southwest Research Institute where I work. This is going to go and explore some of the asteroids that are out near Jupiter. And its goal is to look at some of these most pristine and oldest asteroids to really understand what the solar system was made out of when it was forming. I've mentioned the asteroid Psyche a few times. That's an asteroid that we think might be made out of almost purely metal. And so we want to look at how an asteroid looks close up as a metallic asteroid. So that mission is launching late next year. And there's one more important mission called DART. This is the Double Asteroid Redirection Test. It's also going to launch later this year. And its goal is to go to an asteroid that has its own moon. And it's actually going to crash into the moon of that asteroid so that we can test whether or not we can actually physically move or change the orbit of an asteroid if we ever need to, because one is on its way toward the Earth. So this is a really exciting opportunity to demonstrate whether or not humans could be in control of our own fate when it comes to asteroids and planetary defense. And so I think that is all of my slides for today. So I'm really excited to hear any questions y'all have.
Well, thank you, Dr. Becker, for your presentation. It was a lot of great content about asteroids. But before we go, swing it back to Andy, I would like to ask the audience, so based on Dr. Becker's presentation, I'll have a poll question to launch. And the poll question is, so based on her presentation, which of these is true about asteroids? Which of these are true about asteroids? And we will give you a few seconds to answer. All right, numbers are running up now. All right, awesome. Thank you for your participation. This is great. So let's do a countdown. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Awesome, awesome, awesome. So I'm going to end polling. All right, Dr. Becker, how did they do?
I don't think we can see the results.
I don't see the results, no.
Oh,
Yeah.
okay, excuse me. Okay, so the results were all of the above. So the answer choices were asteroid orbit the sun, asteroids are much smaller than planets, asteroids are very old, and asteroids come in lots of shapes, sizes, and materials. So 85% of our guests chose all of the above. How did they do?
It sounds like they did pretty well. Good job, everybody.
All right, woo! Awesome. That means that you did an awesome presentation. So thank you again, Dr. Becker, for the information. Now we're going to swing it back over to Andy to check on his results.
I'm just going to jump in real fast. Thank you guys for participating in the poll questions. We want to remind you that since it's a webinar, you're not going to be able to unmute yourself to ask questions later. So if you have questions for Dr. Becker about asteroids or any questions, really, we ask that you put them into text. And so the way you can do that is at the bottom of your screen, you have an option for Q&A. And if you open that up, you can type a question in and we'll be able to see it and answer it. If you have trouble finding the Q&A, you can also put your question into the chat. But that's the only way we'll be able to take your questions. So please start putting those in and then we'll have lots of time to discuss. Okay, now Andy, please tell us about your results.
Okay, so I actually looked at the participant list during the presentation, and now I'm really nervous just based on some of the names I saw on this, but welcome everybody, and here we go. All right, so let me get this camera going so we can look at our asteroid models again. Okay, so there we are, asteroid models 1 and 2, about the same size, about the same volume, a little bit different shape, but we're wondering, what do the interiors of these look like? And as I mentioned, you can kind of take the temperature of the asteroid, if you will. That's one way to determine what the structure is like. And like Dr. Becker said, the asteroids can be these solid objects, or they can be what we call rubble piles, where it's just these little pieces held, or relatively little pieces held together by gravity. So what I did, or what I didn't tell you about our model asteroids here, is I had it in the freezer, had them in the freezer over the afternoon, and brought them out. And when Dr. Becker started presenting, I started taking their temperature. I chose the same spot on the top of each one of both, and just use one of these laser guns you've probably all seen, especially over the past year. If you had to go into a hospital or something, you took your temperature, and just took temperatures, and I recorded them. So let me share that data with you all. Okay, here it is. So asteroid 1 was on the left, asteroid 2 was on the right. And as I took their temperatures every minute for about 10 minutes, here's what happened. So they both were warming up, which of course you would expect, take them out of the freezer. Asteroid 1 warmed up a little slower, not as quickly. Asteroid 2 really got off to a roaring start there, and then slowed down a little bit, but it still kept going. And of course, they were starting to get close to the room temperature here, where I am, so it really didn't change a whole lot. But this is an idea of how asteroids, or any object really, but objects that are solid tend to resist warming up or cooling down. It takes them longer to do either one, whereas objects that are more loose, like gravel or little pieces of rock kind of held together, those will warm up or cool down quicker. So based on what we see here and that idea, what do you think about asteroid 1? Do you think asteroid 1 compared to asteroid 2 is solid, or do you think has Dr. Becker called a rubble pile? What do you think? Tell us in the chat. Yes, please. So 1 or 2, do you think 1's a rubble pile or a solid? Got to get to the chat box here. There's the chat box. Don't be shy. It's okay, we got to vote for solid. Okay. A rubber pile. I love that. Asteroid 1, a rubble pile. Okay. Well, I'm not going to open these because it'd be a mess. But so asteroid, our model 1, actually, it's a solid rock. It's a solid piece, a solid rock. And our asteroid 2 is a rubble pile. It's actually just a pile of sand. And they're both a pile of sand and a rock. If you're curious, I don't know what kind of rock 1 is because I didn't make it. But so 1 is solid, and number 2 is a pile of sand. And we wrap both of them up in aluminum foil. So we're just demonstrating this idea that solid objects will heat up and cool slower than loosely consolidated rubble piles, so to speak. So there we go. And if you're interested, that term, I really didn't want to use it, but I'll throw it out there. It's called thermal inertia. So that's one characteristic of asteroids we can determine through more complex means than these laser thermometers to determine what their interior is constructed of. And that's a really important thing to know. It's just good to know in terms of science and asteroids. It's also really good to know if we need to do something about a potentially hazardous asteroid. Okay, I am done.
All right, well, thank you, Andy. Before you follow up, Dr. Becker, I want to go ahead and address the questions in the Q&A. And while let's go ahead and do that. So this question comes from Mr. Christopher. That's our guest tonight. Thank you again for joining us. And he asks, what is the oldest asteroid?
Yeah, that's a great question. I don't know if we know one particular asteroid that's necessarily older than all the rest, but that we do have classifications of asteroids. And we think some of these asteroids that are a bit further out, especially those that basically got trapped in a gravity well of by Jupiter in a resonance location with Jupiter. We call these the Trojan asteroids. These are asteroids that basically kind of always kind of orbit a little bit ahead or a little bit behind of Jupiter. We think they've been there for a really, really, really long time. And so we think that these ones, they're farther out from the sun, so they're not really getting melted. They're not really potentially getting as many impacts. We really think these are sort of the oldest asteroids that would be good to study. And so that is what the Lucy mission will be going and exploring. It'll go look at several of those asteroids so that we can really unlock those origins of the asteroids. And that's sort of why the mission is called Lucy, just like the first sort of proto-human was Lucy. This is what that mission aims to do, is look at those kind of earliest forms of asteroids.
Okay, and thank you. Another question comes from Asteroid 14593. What are you going to do with your research now that the Hubble telescope as well as the Arecibo telescopes are not functioning? What are you going to do, Dr. Becker?
Well, my fingers are still very much crossed for the Hubble Space Telescope to come back online. And there's also a lot of emphasis and excitement about a rebuild of the Arecibo Observatory, which I also hope takes place. In the meantime, there are a lot of other telescopes to look at asteroids with. Although without Hubble, we do not have any UV capability to study anything right now, especially asteroids or anything like that. So that will be a loss for me, especially because I'm mostly a UV scientist. But I have a lot of other projects as well. Like I said, I do rings and I study Jupiter's moon. So I'll find ways to keep busy. But it is every time we see a loss of an important facility, it's upsetting, and there is ultimately a loss of science. And with Arecibo, one of the biggest losses was the planetary defense component. So we do have Goldstone radar to look at some of the asteroids, but Arecibo was the Arecibo Observatory in Puerto Rico is much bigger. It had a lot more flexibility to go in kind of anytime we saw a good asteroid, we pointed at it, we'd get the radar, we would know exactly where it is, just like a police gun, like a police radar gun could be used to see how fast a car is going. We could do exactly that with an asteroid. And so it is a big loss to have both of those telescopes offline right now.
Right, and I thank you for sharing that. Our sentiments is definitely with everyone that relied on that data. So I thank you for bringing that up, and we hope that you hear some great news soon. And so we have another question from Roselle. So thank you for submitting your question. Their question was, how many asteroids do we know of?
Oh, that's tough because there are. It's many thousands of asteroids.
Mm-hmm.
There are some really cool YouTube videos you can look up to see sort of the discovery pace of asteroids. And ever since we put some of these surveys online now, where we can actually look at tons of asteroids every night, we discover more and more with some of the surveys that we have here on Earth, and also some of the ones we've put in space. So, there are many tens of thousands that we know of, and there are probably significantly more that we just haven't seen yet.
Oh, wow. Okay, so that's incredible. And that's why we need each and every one of you to be our future scientists, right? So to discover those things that are unknown. And so we have a YouTube question, and thank you everyone that's listening to us on YouTube. Thank you so much for your question. And it says, how has NASA's DART mission adapted after replacing an ESA and AIM mission?
So some of you out there are clearly also experts, or at least tangentially experts in this.
They're posing as children.
Yeah, so the idea originally for this mission, and I'm not involved in it, so I may say a few things wrong here, but my understanding was that the original plan was to not only we're going to send an impactor into the satellite, the moon of this asteroid. But ideally, wouldn't it be great to also have another mission out there watching and taking pictures? And so that was what the ESA, the European Space Agency's mission, was going to do. I don't know if I know that there has been changes in that status. I don't think there will be a spacecraft out there, but I don't think that's 100% off the board yet either. But either way, we have the facilities here on Earth to monitor how that little asteroid moves. So we will use radar from Goldstone, and we can use visible telescopes and other telescopes to see and track how the little mini moon moves as a result of the impact. So there's just other ways that we'll monitor the results of that experiment.
Okay, well, awesome. We're gonna take it back over to Andy's activity and see if we can get this question answered for Russell. Would an asteroid primarily metal change temperature faster also? So I guess if a asteroid was primarily made of metal, would that change the temperature faster?
Yeah, so Andy, did you want to take that or did you want me to go ahead?
That is all yours.
Yeah, so I will say composition will certainly matter. Yeah, so if you're going to have things that can heat up and re-radiate that heat faster, it's going to have a bigger, it's also a very important factor on how much of the thermal emission you might see. And I'll also note a lot of that is also going to be very much on the surface layers too. So you're really kind of, those infrared measurements are really going to be looking at kind of how the surface is heating and re-radiating that heat from that it's getting from the sun. And certainly, yeah, if you have a metal object, it's gonna do what we know metal to do, which is when you touch it, once it's hot, it gets real hot.
Yes, and so I know that we don't know how many asteroids there are, but possibly, or we don't know the oldest either, but could you talk about the first one that was discovered?
Sure. So I actually had an image of that one. The asteroids are actually numbered, so you kind of can get a sense of how many asteroids there are if you know a few of the names of asteroids. The first one is called 1 Ceres. And so that was visited by the Dawn mission, NASA's Dawn mission. And it is, we discovered that before we discovered some of the planets. So at first that was actually considered to be a planet. And then it was changed to an asteroid when we realized there were sort of all these other asteroids or similar sized objects kind of orbiting in the same area, although Ceres is the biggest one. So just like Pluto changed its status from a planet to something else, Ceres also actually had that same exact scenario happen to it, a little over 100 years ago or so. But Ceres is a really exciting world. It's a pretty solid, round-ish kind of asteroid, and we do think we've seen indications of possibly some sort of liquid or salty liquid underneath its surface, which makes it a very exciting place to study.
Oh, wow. Grace pulled some excellent facts around Ceres, and one of them was that it's the largest asteroid to be discovered at 580 miles across. The smallest known asteroid is just 6 meters or 20 feet across. Is that correct information, Dr. Becker?
I would assume she knows better than I do. I don't have all those numbers on my head.
Well, that's pretty incredible, right? Go ahead, Grace.
That's amazing. No, I have a question from higher up in the chat. So Harold asked, Ryugu looked a lot like Bennu. Was that intended when the mission to Bennu was launched? They both looked like rubble piles with an equatorial bulge.
Again, more experts using things like equatorial bulges,
right.
But yeah. So again, I'm not part of either of those missions, so I can't speak 100%. But from my understanding, they were a little bit surprised. Everybody was a bit surprised by how much they looked so similar. That shape of asteroid, these, for these, what we call near Earth asteroids, these are asteroids that are closer to the Earth than the main asteroid belt. It's pretty common to see that shape of an asteroid, to see this kind of round thing with a bit of an equatorial bulge around it, being like almost like a belt around the center. So it's not shocking that they looked somewhat similar, but I think just how similar they looked was a little bit surprising. They are different classifications of asteroids, so which is indicative of what they're made out of. So there was probably some indication that they thought they were going to be a little bit different from each other, but it was kind of surprising and I think exciting, because that means we have 2 samples from 2 different asteroids that may or may not be very similar once you actually can put parts of it under the microscope. We see the bigger picture with the spacecraft itself. And now we'll get to see really up close what that might mean and what are the subtle differences that we can't see even from being as close as we are with the spacecraft.
Yeah, absolutely. It's going to be so exciting to get those samples back. Can you tell us the difference between an asteroid and a comet?
Sure, yeah. So sometimes sometimes the line is blurred there. But for the most part, comets are objects that are coming from a bit further out in our solar system. They have a lot more what we call volatiles. So they have more like water and frozen carbon dioxide. And as they get close to the sun, because they spend most of their time kind of farther out, they stay frozen and icy. And as they get closer to the sun, they heat up. And then they go through a process called sublimation, which is instead of going from, if you have like an ice cube, usually if you warm it up, it melts and then it might evaporate if you keep warming it up. This gets so hot so fast that it goes straight from kind of icy state to gas state. And so we call that sublimation. And so when comets start to sublimate, once they get a little bit closer to the sun, that's when we see those nice, beautiful tails that we can often see and that we think of with a comet. And that's all that gas kind of coming off of the comet and then the solar wind kind of pushing it in the direction away from the sun. And so that's the main difference, is really just the icy component of a comet, then whereas the asteroids are really more of these rocky, maybe metallic surfaces.
Okay. So you also, not just that the volatiles are more present on comets, they have more water and ice and steam, I guess. What about, you said the comets also typically are farther out in the solar system. So where do asteroids typically live?
Yeah, so most of the asteroids do typically live in that main asteroid belt between Mars and Jupiter. So that's where we find most of them, although there are tons of them in near Earth space, again, where we're calling near Earth asteroids. That doesn't mean that they're like really, really near the Earth, but it means that they can come a bit closer than the main asteroid belt is. And the comets mostly are formed and can live out in what we call the Kuiper belt, which is out where kind of Pluto is, or even farther, which are in the Oort cloud, which is like a third of the way to the next star. You can be really, really far out and still be a comet that comes to our sun.
That's
Oh,
so
wow.
cool.
Go ahead, Grace.
I was just going to follow up on that with one more question about the asteroid belt. So that's that space between Mars and Jupiter, and we've sent spacecraft through the asteroid belts, right? So my question is, when we're picturing the asteroid belts, when we see it shown or like asteroid fields shown in movies and stuff, and there's asteroids everywhere and you have to maneuver really carefully, is that what our asteroid belt looks like?
No, that's a really awesome question, though. And I'm glad I thought about having a slide in there, but I didn't want to go down that rabbit hole too much during my 10 minutes. But no, that's exactly right. It is not like what our asteroid belt looks like. Even though there are these tens or hundreds of thousands and maybe even millions of asteroids in the main asteroid belt, they're so small and space is so, so, so big that these things are all very, very, very far apart. So collisions did used to happen between asteroids in the main belt when there was a lot more stuff in the early solar system. But now collisions are quite rare between objects because they're just so, so far apart that they don't usually run into each other. And therefore our spacecraft also don't run into them on their way out to Jupiter, Saturn, or Pluto. Fortunately for us, yeah, it's not a minefield where we're like dodging asteroids to get out there. It's we have to work hard to be able to pass close to an asteroid on one of these missions.
All right, I want to take a question from our chat box, and then I'm going to go back to Q&A. Are comets considered shooting stars?
Oh, that's an excellent question. So comets are what, we can imagine, we've seen drawings of them that date back to, many hundred, thousands of years ago, because people have been seeing comets for so long. But they are not what we consider shooting stars. So shooting stars are actually, they can be related to a comet or an asteroid. And basically what a shooting star is just a piece of rock, or could be ice. It could be any little kind of fragment of these asteroids or comets that enter our atmosphere. And as they enter our atmosphere, even though they're really tiny, they can be quite small. They get so hot as they come into our atmosphere, the friction from the atmosphere itself burns up those material. And that's what we're seeing as shooting stars. So every time you see a shooting star, it's actually just the burning of possibly something that's small, like the size of a small rock, entering our atmosphere and burning up. The comet itself, you would see night after night after night. So last year, there was a good comet that was visible by sort of to the naked eye if you were in a really, really dark place. But with a decent pair of binoculars, I was able to see it from here in San Antonio. And you know, those you'd see night after night after night. And that's a, you know, you'd see that comet. But the shooting star you just see for that instant, and then it burns up and then it's gone.
All right. Well, speaking of something burning, in the Q&A, we have quite interesting question from Gregory. What happens if you paint an asteroid white while it's flying towards Earth?
So I think I understand where the question is going. So the idea is coming up with ways to best protect the Earth from an asteroid that might be on its way. And so the DART mission's goal is to test the idea of basically smashing something into it to move it out of its current trajectory. And all we have to do is change the trajectory kind of just a little bit so that that asteroid doesn't stay on its path towards the Earth. One other possible way to do that is to change how it re-radiates heat. And so painting something white or painting something black, just like, you know, if we're, you know, on our driveway, and if you have a, you know, a blacktop driveway, that can be really, really, really hot, and it can heat up and it can change. White reflects light in a different way. So we can, if we can change sort of the properties of the asteroid itself, perhaps that can move it in a different direction and then get it out of our danger zone. It hasn't been tested yet, right? But it all kind of actually goes back to Andy's experiment, which was changing how these objects reflect or re-radiate the heat, and then that can change how they spin, and it can change a little bit about their orbit. So it's possible that if we did something like that, we could end up nudging it in a different direction. The test would be, you know, how long does it need to be painted that color, and how close does it need to be to the sun for that to really start to actually make a significant amount of movement that we would feel like we're in the safe zone. But theoretically, yes. I mean, changing the properties of the asteroid could change its trajectory.
Thank you for the insight into that question. I was reading it and I was like, I don't understand. But you totally, yeah, I totally got and connected it to the experiment. That makes a lot of sense.
I'm pretty sure that's where, again, there's a lot of hidden semi-experts or full experts out there, like pepper in with questions here.
Well, so we're getting to about 15 minutes left. So final questions, please put them into the Q&A and chat. I'll ask one question while we're waiting. Speaking of stuff burning up in the atmosphere, I've heard the terms meteor, meteorite, and meteoroid. Could you tell us what's what?
Yes, I think. I hope I get it right. So, right. So an asteroid is when it's out in space. All those terms are basically location dependent. So asteroids while it's out in space, meteorite is when it's on the ground and you can pick it up. And meteor is when it's in transit. So that's when it's kind of in that shooting star stage, when it's in our atmosphere. It's called a meteoroid, or it could be called a bolide as well. It could be a meteor and a bolide. And I think a meteoroid is sometimes just used to mean a smaller asteroid.
That's what my research showed.
Yeah. So
Thank you for
asteroid
confirming.
is in space. Meteoroid is kind of a smaller asteroid that's maybe something that could potentially come into our atmosphere. And then meteor is while it's in the atmosphere, and meteorite is it's on the ground.
Thank you.
I don't know. Somebody can double check me on NASA research.
That's perfect. Thank you. Okay, well, we have another question in the Q&A from Shelley. who says, I always thought it would be neat to hunt for meteorites, correct term, meteorites in the desert. Any tips as to what to look for?
Maybe to bring me, because that sounds awesome. But as a non-meteorite expert, the key that, you already have the location right. If you're in the desert, if you see anything that doesn't look like desert, is kind of like, that might be a piece of meteorite. So that's why a lot of meteorite hunters go to Antarctica or they go to the desert, because it's pretty standard what it should look like out there. And if you see kind of anything on top of the sand or on top of the ice, it's probably been dropped there recently from space. Whereas a lot of people might be in their backyard and see a cool rock and be like, is this a meteorite? And then they try to hunt down a professor and a scientist and ask them like, oh, look, I found a meteorite. And then it's like, no, it's just a rock in your yard. But going to the desert or going to Antarctica gives you the opportunity that really anything that looks out of place has a much higher potential for being a meteorite. So I don't personally have any other advice beyond that because I've never gotten to do it. But if you're really interested, you can send me a message and I can connect you with some meteorite hunters.
Well, that would be super cool. And so I thank everyone for submitting their questions. Phenomenal questions came through. And thank you, Dr. Becker, for being a trooper with tackling them on head first. So thank you for that. So we have a few more questions for our guests, for our attendees. And so I'm going to launch our last poll question, and then we're going to provide some resources for everyone in attendance. So I'm going to go ahead and launch our last poll question. What would you like to learn more about? What would you like to learn more about? And then this way we can provide more of those virtual programs to fit your needs. What would you like to learn more about, everyone? Okay, we have NASA mission and human exploration. Stars and galaxies are kind of fighting. It's like a race right now, right? It's kind of going back and forth. Planets and moons, and then the rocky Rubble Pile activity. Awesome. Grace and I kind of predicted that, right? Awesome. Love it when a plan comes together. Awesome. 5, 4, 3, 2, 1. Awesome. Thank you, everyone, for participating. And I did say that was our last one, but I thought the questions were together. So there is, I'm going to stop sharing that. And then this is the last one. What did you like more about tonight's event, everyone? The scientist presentation, asteroid demonstration, which Grace, would you please drop the link in the chat box for the rocky Rubble Pile if you have not already done so? Thank you. And Razel, if you do have more than one answer, drop it in the chat box. Drop it in the chat box if you have more than one answer. Thank you so much for participating, everyone. Thank you so very much for your attendance tonight. And Zoe Hernandez, you have your hand raised. Go ahead and drop your question in the chat box, if you will. Thank you for raising your hand. You are appreciated. All right, and for this poll question, we have learning something new about asteroids. Way to go, Dr. Becker. That was what they liked most about tonight's presentation. So phenomenal job, everyone. Last but not least, I'm going to send up our PowerPoint where you can learn more about tonight's presentation. So thank you for joining us all for Asteroid Day. We made it. Woo! Awesome, awesome. If you want to know more about our virtual exploration experiences with planetary scientists, please visit either our YouTube page or the link lpi.usra/education/events/VEEPS. We will always be there to answer your questions. And if we don't know, guess what? We have experts that will be able to provide an answer if they have it, if there is an answer to your question. So, ladies and gentlemen, I bid you good night. Thank you so much for attending our event tonight. If you want to know more about our future events, join our newsletter. We send them out every time that there's a new event, and you will get an alert that there is one, and go ahead and register and join us. If you have any other questions for myself or Dr. Becker, please email her. She said that she's open to emails. Everyone, have a good night, and thank you so much for joining us. Bye, everyone.